Let's take a look at RSA first. The algorithm is not a new development. It was created back in 1977. It's not the first asymmetric algorithm either. The first application of the asymmetric cryptography scheme was Diffie-Hellman's Secure Key Exchange Protocol. The Diffie-Hellman key exchange is still implemented today, for example in public key infrastructure and IPsec. This solution solved the problem with exchanging confidential data through an untrusted channel while keeping the confidentiality of the data. The point was not to send a key, which should not be done, but to send a challenge, a random message, instead and receive a response. Both parties make computations based on the challenge and response messages. A first user picks a key and generates a challenge. The second user picks a key, receives the challenge, computes something based on it, and generates and sends a response. Both users assume that they have provided the same key. The result of the random key generation was the same combination of digits. Let's go back to RSA. The algorithm was granted a patent that expired in 2000. To be able to use it before that time, a license fee had to be paid. The patent rights were given to RSA Data Security. On the expiry, the RSA algorithm has been implemented in a number of solutions and software. The basis for the operation here is key generation. The encryption and decryption steps are relatively uncomplicated. Remember that the key, the ciphertext, and the plaintext will be numbers. You can represent any string as a number. This is how computers operate. Let's consider the key generating mechanism. You have to pick two large primes. The values have to be large enough to be represented using 1024, 2048, or preferably 4096 bits. In this presentation, we'll pick the standard prime numbers 7 and 11. Compute the product. It's 77. The next step is to find an exponent that satisfies an equation where the greatest common divisor of the exponent and the product of the two primes minus 1 will be 1, as in the following formula. This equation has many solutions. In practice, the smallest found e is usually chosen. The value e has no bearing on the security of the ciphertext. The smaller it is, the faster the encryption will be. For the two primes we picked, you can choose e equals 37. In this way, you have found your public key. The public key is made from the values n and e, 77 and 37. Now a private key that corresponds to the public key has to be generated. The private key will be generated based on the following equation. You have to multiply e and d in such a way that you find a product of multiplying p minus 1 times q minus 1 as a modulo operation parameter. For the values we calculated earlier, d can be 13. The value d will from this point be your private key. It amounts to 13. Why is this all working? From what we officially know, finding the values p and q based on the value n is computationally complex. As it turns out, while we're able to calculate the key d by having the product, if we don't know the values p and q, we must resort to checking all possible solutions to the equation. This is presumed infeasible because they are large prime numbers. Encryption itself is easy. It involves assuming that the plaintext has a value that is a bit smaller than n. Next, you perform a modular exponentiation. The ciphertext you get is the plaintext raised to the e power, modulo n. The values E and N are parts of your public key. If the plaintext was 2, the ciphertext will be 51. Decryption is inverting this process. To decode the ciphertext, raise C to the D power modulo N. In this way, the result will recover 2.